All right, friends, we are back at the College of Southern Idaho, Evergreen Building, and the Geology classroom. And this is going to be our first video on the igneous rocks. And what we're going to start with is a overview of the igneous rocks, because to identify igneous rocks, you really need to have a good handle on the texture of the rocks, which we'll look at, and the composition, because that's our primary two criteria that we use to classify igneous rocks. This is not an igneous petrology class, and so we are not going to go super detailed. You can get deep in the weeds. There's literally dozens and dozens of different igneous rock types. We're going to stick with a more Geology 101 generic classification, but I think that'll help most of you with maybe not only determining your rock names to some degree, but more importantly, at least for me, is figuring out the story of the rock and figuring out how the rock came to be, what sort of environment it formed in, what were the conditions, because to me that's much more valuable than just knowing the rock name. But nonetheless, we'll try to tackle both of those as best we can. So let's just dive right in. Some notes I have here. Yeah, not an igneous petrology class. That would be a class you would take maybe at a 300 level or maybe almost a graduate level if you were a geology major. We're going to mainly stick with these two things because igneous rocks, their story and their names can be largely derived from their textures and their composition. So when I say texture, I'm not talking about how the rock feels in your hand. I'm talking about the size, shape, and arrangement of the minerals. So how big are those mineral crystals? How are they arranged? What sort of fabric is in there? And then when we look at composition, we're mainly looking at what minerals are in the rock themselves. And this is a reflection of the chemistry of the original magma or the lava that produced the igneous rock. So we're looking specifically at the minerals that make up the rocks. But we'll see that there's some fairly simple ways that aren't always a slam dunk, but good ways of determining mineral composition might be things like looking at the overall color of the rock. So what we're avoiding, but you can dig into these if you want to on the internet. So if you want a deeper dive into igneous rocks, we mainly determine igneous rocks in terms of their mineral composition, and we use these fancy diagrams that look like pyramids called ternary diagrams to figure out the exact name of a rock. And you'll see lots of numbers on here. These are actually percentages. So this would be 100% quartz. P is for plagioclase. A is for the alkali feldspars, so like the potassium feldspars. And the Fs are from these other groups of minerals like nepheline and what are called sometimes the foids or the feldspathoid minerals. We're not going to dive into this. We are not going to cover syenite and quartz monzonite and monzo granite and everything you're seeing here. I'm not going to go to that kind of level of detail because to determine these percentages, what you have to do is actually figure out what percentage you have of each mineral in the rock. And for the most part, that's hard to do with just a simple sample you have in your hand. It takes more of an in-depth analysis, microscopes, that sort of thing. But realize these things are out there on the internet. So if you want to know what a percentage of minerals you have in your rock and you're pretty good at identifying minerals, you might look for a mineral composition diagram like this that kind of shows you roughly what 20% of the volume of the rock would look like, 30 for 50. And then you can look for these ternary diagrams too if you want to deep dive. So we'll get rid of that because we're not going to look at that much. So what are we going to look at? We're going to start with textures. So again, this is the size, shape, arrangement of the minerals. The textures are important because they tell us a lot about the cooling rate of the magma. They tell us whether the magma, superficially tells us whether the magma cooled slowly underground, maybe miles beneath the Earth's surface, or if that magma erupted from a volcano, so it's lava now, and cooled more quickly at the Earth's surface. So the way the minerals are kind of put together and their sizes is very instructive. And we're going to use some fancy terms here, but these are terms that if you're real serious about this, it'd be great for you to kind of get in your lexicon and try to learn these as best you can. Ultimately, though, you could pass on the fancy names as long as you know what to look for and what these mean. So let's start with the first one here. So this is pronounced Phaneritic. So a Phaneritic igneous rock texture has big crystals. When we say big, we need to define the size. And so let's say for simplicity's sake that anything bigger than 1 millimeter. So basically, if you can see visible minerals in the rock, crystals, and they're interlocking. So this is 2 important considerations here. They've got to be big enough to see, but they're all squished together. They're sharing boundaries together. They're squished together like a mosaic. What this means is that this is a slow cooling process. So basically, as the magma is cooling slowly to give us this phaneritic texture, the elements have more time because of the slow cooling to nucleate and form larger and larger crystals. So slow cooling in magma means that we're going to have bigger crystals in the rock typically. And that's an important thing to make sure you understand, because that governs a lot of what we're doing. There are some other factors that play a role as well, like the presence of water and fluids, but we're going to, again, stick to the basics. Sometimes you see this term, and I might have used it in one of the past videos, a pegmatite or pegmatitic texture would be a phaneritic texture, but instead of just being large enough, just over 1 millimeter, these are exceptionally large crystals. So this would be something where we have greater than maybe 1 centimeter or so. So let's look at both of those there. I've kind of laid out a couple of these here. Let's start with just a nice phaneritic texture. We've maybe seen this rock before, so we could start with this one here. But we can see you got my finger in there for scale, or what else could we use here that's kind of handy? Oh, here we go. This is even better. We've got well, it's hard to see maybe through it. Let's just use a pencil tip. I think that will work good for sort of a scale. But we can see we've got big crystals in here. We've got some pink potassium feldspar. There's some black shiny biotite. There's some kind of smoky gray, somewhat translucent quartz in here. A little bit of plagioclase, which is the white stuff. But the point is, all these crystals are big enough to see. You can see their size relative to my mechanical pencil here. They're all greater than 1 millimeter, and they're all interlocking. They're all sharing borders and boundaries, and they're all sort of squished together. So that's a nice classic granite, and we'll get to the rock names later in future videos. We'll go through each, maybe not each, we'll bundle them up together, but we'll go through several different rock types. So there's a nice phaneritic rock. Here's another one. A little scale here with the pencil. So you can see these big crystals all sort of stuck together. Here, this one gets a little tricky. We can see these 2 lighter ones have some dark minerals. And so the contrast between the minerals and the size of the crystals is pretty easy to ascertain. But you get to a rock like this where it's very dark, and it's hard to see the individual crystals. But when I rotate this in the light, you can see some little flashes of light. There's a really nice one if you watch right here. As I rotate that in the light, you can see that little surface reflecting the light. And remember when we talked about minerals and mineral properties, that one of the properties of a mineral is cleavage planes. So basically by rotating this rock in the light, we can actually see the size of the crystals by looking at the surfaces reflecting in the light. And you can see that these surfaces here, right by my finger here, are definitely more than 1 millimeter in size. And they're all squished together. It looks like they're interlocking. So this would also be a phaneritic texture, much like this one. But obviously the composition's different, right? Very different color, different mineral distribution there. And then we have one here, a similar sort of thing, mostly just kind of black and white. But we can see the crystals are all kind of squished together and sharing borders and spaces together. And then for pegmatitic, we can see these crystals are much bigger. We can see there's some flaky muscovite in here. That's what's kind of this shiny material here. These black minerals, this is actually tourmaline. So we have some larger tourmaline crystals, and then big sections of quartz in here. There's a nice muscovite kind of shining right there as well, a little muscovite crystal. But you can see the crystals here are much larger than in this phaneritic rock here. And so this, because the crystals are of a size greater than 1 centimeter, so we would call that pegmatitic. Let's go to our next texture. So our next texture is, well, what if the crystals are really small? What if they're generally all less than 1 millimeter or so? Well, this is what results from very rapid cooling of lava. So this would be a rock that erupted at the surface, came out of a volcano. The lava cooled very quickly. The minerals and elements did not have time to get together and make bigger crystals, and so we subsequently get very rapid cooling and smaller crystals. So notice that the first thing we've learned here is just by looking at the size of the crystals, you can infer the relative cooling rates and therefore the environment, whether it's under the earth in a magma chamber cooling slowly, or erupted from a volcano. So what do our aphanitic rocks look like? Well, here's one here, again for scale. So we can see some mineral specks in here, right? We can see, hopefully this will focus for us. Can I zoom in? Maybe, maybe not. There we go. That's not bad. So notice how much bigger the pencil tip is now. So these little black specks and even these white ones here, that little kind of squarish thing, these are crystals, but they're much, much smaller. If we zoom back out, we can see some of the sizes of these things. So this would be more of an aphanitic texture. There might be a couple crystals that exceed 1 millimeter, but by and large, most of the crystals that make up this rock are in the small range. Another one I have here, if I can kind of prop it up so it's oriented well, would be this darker one here. We might even zoom in. Yeah, and so again, just really, really fine-grained, right? You might see a few little flashes of reflection. Those crystals are much, much smaller though. So those are our aphanitics. We have phaneritic and aphanitic. Let's look at some variations now. So our next one is what we call porphyritic, or sometimes you've maybe seen rocks called porphyries. These are actually pretty common in some mining and economic geology applications because they oftentimes have ore bodies in them. So porphyritic is actually going to kind of be a blend of these two. We get big and little crystals. And what that implies is that there's different cooling rates happening. So remember, our big crystals are slow cooling and our small crystals are fast cooling. So what we might expect then in a porphyritic rock is a magma body that starts to cool slowly, creating these big crystals, but then ultimately it gets pushed towards the surface, the magma erupts, the big crystals that have already formed get carried with the magma up to the surface where the rest of the molten material cools quickly and gives us these small crystals. So here's some examples of some porphyritic rocks. And these are quite common in a lot of volcanic environments. So we can see this has big crystals. These big white crystals are quite large, but they are, let's see if it'll focus here. They are sort of embedded in this much finer grained material. So everything sort of surrounding it is much more fine grained. Move it over here. There we go. Okay. So this would be a porphyritic rock here. I've got another one right here. Again, we've got some of these big white crystals, but there's also some, they're not nearly as big, but there's also some of these black crystals in here as well. So these are both porphyritic. Here's a little bit different one here where the black crystals are the big crystals in here. We sometimes call these big crystals phenocrysts. So if you need a fun word for the day, you could do that one, phenocryst. So this has big phenocrysts of amphibole, these big black crystals, but everything else in here, if you look at the area between the crystals, it's very fine grained. So it's not phaneritic because we don't have all big crystals squished together. We have big crystals floating around in this more small or finely crystalline matrix. And here's one last one here where we have these, sorry, working on the camera here. Here we go. We have these clusters of white crystals that are much larger, and then all the black stuff's incredibly fine grained. We can't even see how small some of this is. We also have some bubbles in here, which we'll talk about. So that's our porphyritic texture. Talking about vesicular. So the gas bubbles we see in igneous rocks are called vesicles. And so a rock that has a lot of these vesicles it has a texture that we might call vesicular. So a couple examples of that might be this rock here, kind of your typical, what most people would call lava rock, kind of dark colored, but it has a lot of these holes in it. Another example of a rock I would consider to be vesicular, has a lot of holes in it. It also has another texture in here, so it's possible to have more than one texture. We can see some really nice green olivine crystals in here. So you might call this porphyritic or slightly porphyritic because it does have some bigger crystals floating around in this dark gray material here. And just so we can see that the rocks do not have to be dark or basaltic, here is a highly vesicular rock. This is a piece of pumice, which we'll spend some more time with. If we kind of turn it on end, we can kind of zoom in here and see all the holes in this rock. The holes are a little bit different though. They're actually kind of stretched out. It's almost more like meringue or froth, if you will. And when you pick this rock up, it's incredibly light. but you can see a lot of the kind of stretched holes and bubbles or vesicles in this rock as well. So a couple different vesicular rocks. One texture we have is glassy. What can I say about glassy? It looks like glass, it's shiny. Glassy rocks tend to form primarily due to very, very rapid cooling. And our true glassy rocks that we'll spend some time with are the obsidians. And the obsidian rocks basically cool so quickly that no minerals actually form. They're actually unordered elements. We'll spend time more on these later, but this is an example of a glassy texture. And then our last texture here is pyroclastic. If you tear apart this word, pyro means fire, like a pyromaniac or a pyrotechnic show. Clast means rock, so this literally translates to fire rock. So one of the things that volcanoes produce oftentimes is when the lava gets exploded into shrapnel, tiny, tiny shards of torn lava and crystals, we call that ash, the size of the material ash. So if we have an igneous rock that's pretty much mostly made out of ash, then the textural term we use there is pyroclastic, and a couple of pyroclastic rocks. So if we kind of look at this one here, we can see there's some like fragments of rocks in it, but as I kind of hold this and move it between my hands, you can see it's kind of, and they don't always do this. This one's actually leaving a little powdery residue on my fingers because that is all fine ash, volcanic ash. Another one here, you might see a few crystals in there. There's a nice crystal right there. So crystals can be in these pyroclastic rocks. There's actually some pieces of torn up pumice in here as well. And here's another one here, but mostly what this ash is comprised of is ash. So that's a good example of a pyroclastic texture. Okay, so a lot to digest there, but maybe practice your textural terms with the rocks you have. You could even practice this with foods, right? If I go to Dairy Queen and get a Blizzard, that's a great example. Well, the Blizzard I get is an Oreo Blizzard. So I've got my big Oreo chunks in my chocolate ice cream. That's a great example of a porphyritic texture. The big Oreo chunks are like the large crystals, and the fine ice cream material is kind of like the small crystals. So you could maybe apply these to other things. So some rocks might give us more than one texture, and that's okay, but we want to classify or try to name the rock based on the most dominant one. So as much as you can, look at your rock, figure out which one of these 6 terms, I suppose, best fits the rock overall, and then stick with that as you go to try to classify it, okay? So that's texture. Now let's look at composition. So composition of igneous rocks is largely dictated by how much silica is in the rock. And silica is basically quartz, or chemically it's the same as quartz. It's the most common compound in the Earth's crust, but we're going to be able to figure out how much silica the rock has somewhat by the mineral composition. You can also crudely use the color of the rock to indicate the composition as well. So the terms we're going to use here to describe composition also apply to magma types. So you've probably seen some of these before. They actually also apply to some minerals as well. But the 3 big groups we have are felsic, mafic, and intermediate. So felsic magmas are magmas that have a lot of silica, greater than 65%. Just know that it's a high silica magma. It tends to have mostly the felsic minerals. So it's going to have quartz, potassium feldspar, plagioclase feldspar, muscovite. All of these minerals are fairly light in color. So if you have a magma that dominantly has these minerals in it when it cools and crystallizes, and these minerals are all dominantly light in color, then the subsequent rock should be fairly light in color. So this rock, granite, is mostly made out of felsic minerals. Are there mafic minerals in here, dark minerals? Yeah, but they represent a much smaller percentage or portion compared to the felsic minerals that make up most of the rock, okay? If we look at mafic, which is at the opposite end of the spectrum, these are fairly low in silica, and they contain mostly mafic minerals, so the dark minerals. And if you need a review of these minerals, remember I did a video on all of these 8 minerals. So if you are looking at this and it's a little confusing, I'd encourage you to go back and look at my mineral series where we cover these in much greater detail. So olivine, which is kind of that olive green color, pyroxene, amphibole, biotite, these are all blackish or dark green minerals. And so what will a mafic rock look like that has mostly mafic minerals that came from a mafic magma? Well, it will be quite a bit darker. Might look like this, might look something like this, might even look like this or that. These are all mafic rocks. And so generally you can use the color to determine the composition, but color is not perfect. And a good example of that is our good friend obsidian, which is as black as they come in terms of color. So one would tend to think right off the bat that this is a mafic rock, when in fact this is actually a felsic rock. This comes from felsic magmas, high silica magmas and volcanoes. And it's only black because of the little bit of iron impurities that it contains within it. And so it tends to be this darker color. But this is actually a felsic rock by composition, by chemically, even though the color doesn't match up. But generally, as you kind of scan these rocks, you can generally use the color to some degree to figure it out. Another handy way to figure out composition, and you can find something like this on the internet as well, or I'll put these handouts, I'll put a link to these handouts on this YouTube page as well. As you can look at this graph of mineral types and get a rough sense of what it likes to hang out with. So for example, if you know your rock has quartz, and you undeniably are sure that quartz is in your rock, well, you might use a diagram like this to figure out what other minerals are in it by looking to see who quartz likes to hang out with. Who are his buddies or her buddies? What are the other minerals that associate themselves with quartz? And what we see is orthoclase, which is potassium feldspar, plagioclase, and plagioclase actually hangs out with all sorts of minerals, the micas like muscovite and biotite, and then amphibole. But notice that quartz and pyroxene or olivine do not associate together. You do not see these minerals in the same rock generally. And so this is somewhat helpful. So if you can identify one mineral, that might help you figure out this whole felsic, intermediate, and mafic game. We're not going to deal with ultramafic rocks, which are much more rare. In general, the felsic rocks are derived from magmas or lavas that are lower in temperature, so they are not as hot as the mafic ones, which are much higher in temperature. And then I love this shaded bar up here. Notice that there's a gradation here from white through different shades of light gray to kind of medium gray to kind of dark to black. This is kind of a rough, good guide that will generally help you. So if you see that your rock is kind of a light gray color, that's suggestive that it's a felsic rock. But you would want to make sure and back up that interpretation by coming back to maybe a diagram like this and seeing if you can identify some minerals that are in a felsic rock, right? So if I think that rock is felsic and I see quartz in it, then I feel even better about it, right? But if I have a dark colored rock and I'm sure it has quartz in it, well, something's off there, right? Because quartz is oftentimes not found in these mafic or very dark colored rocks, okay? So you could look for a diagram like this, or I'll put this one up. I didn't make this one, I just kind of grabbed that off the internet. So, okay, so let's quickly go through I'm going to reorganize these rocks into compositional equivalents. So let's look at all the dark colored rocks. We've organized them by texture, but now I'm going to put all the felsic rocks together and all the mafic rocks together and all the intermediate rocks together, which I probably need to explain a little bit better. So let's see, that's pretty good there. I'm going to leave obsidian out. Sorry, Chuck. Just for now. So all of these rocks here are felsic. I've got some that are pyroclastic, made out of ash, some that have lots of bubbles in them, but some crystals as well, this pumice, some that are aphanitic, some that are phaneritic, pegmatitic. There's another one that's pyroclastic, but compositionally, these are all the same. If you grind up these rocks and present them to a chemist, they basically have the same chemistry. These are all felsic rocks coming from a magma body, either underground or erupted from a volcano. The only difference here is the texture, right? How the crystals are arranged or the size of the crystals, okay? If we swing over to here, we can see a diversity of mafic rocks. We've got a couple that are vesicular, they have the holes in them. We've got one here with bigger crystals that's phaneritic. We've got one here that actually has two textures in it. We can see the big crystals in it. Sorry, just trying to help get it there we go. We can see the big white crystals in it, but you can also see the gas bubbles, the little holes in it. So this would be vesicular and porphyritic, but nonetheless, it's the same rock. And then we have one here that's aphanitic, right? Very small, fine-grained crystals throughout. So briefly on the intermediate rocks, and then we'll call it a day. So the intermediate rocks, or the intermediate compositions, are going to be in between in terms of silica content. That should make sense. And more or less, they contain about a 50-50 mixture of felsic and mafic minerals. So they kind of run right down the middle here. And this is a crude classification, right? We just classify them into broadly 3 categories. So amphibole is a dominant mineral, plagioclase, which is white, is dominant, but you don't get much potassium feldspar. You oftentimes don't get much quartz. You don't get at all any olivine. So you can kind of see the distribution of, and you can kind of see that overall it might give you kind of a medium gray. It says purple here, but gray is probably the more common color here. Overall kind of medium gray shade there. And so these are all intermediate rocks. This one is beautiful because it shows us a phaneritic texture, but also note, please cooperate. I'll just stick you in this little seam there. There we go. Also note that this rock has kind of a nice diversity of white and black crystals. It looks like salt and pepper, right? Like there's just as many felsic or light colored minerals as there is dark mafic minerals. So this is a great example of an intermediate texture. These rocks here, which are all porphyritic, are kind of like a medium gray. The shade of gray changes a little bit, but if you sort of take all these big crystals out of them, they're kind of in the same ballpark in terms of the shade of gray that they are. So these would be intermediate rocks. So hopefully that's helpful. A lot to digest. Hopefully you took notes. There may or may not be a quiz later. And then moving forward, these are the rocks I plan to cover. I don't know that I'm going to do, I probably will not do a video on each one. Some, like basalt, I will give them their own video because they've got so much diversity. I may package a few together, but in the future, look for these rocks to be covered in some detail, showing lots of examples, explaining some of the variations we see therein. So hopefully this was helpful. Texture, composition, those are the buzzwords for today. That's what I want you guys to focus on, is practice identifying your igneous rock textures, and then try to also determine composition. Composition can be based on color to a degree, but we want to be a little bit careful because we know some rocks, like obsidian, can burn us a little bit if we're too casual with using color as a guide. We want to use mineral composition more than color if we can. So for now, hopefully that's helpful. That's another video, this one on igneous rocks, sort of your primer on igneous rocks and their textures and how to distinguish one from another. Hope these are helpful, and we'll see you next time. Thanks, friends.